Okay, now we come to the last lecture in the series of Introduction to Cable-Stayed Bridges. After we had the different type of, say, beam material, we now come to special systems of cable-stayed bridges, which are other general type. Until now, we had the regular 3-span cable-stayed bridge. We had a large center span and smaller 40% side spans. Maybe also in some cases just 1/2 of this 3-span, but it has basically the same load transfer. But there are other types. First of all, we can put several towers with large main spans, so not the 3-span, but 5-6 spans in there. We do not have the side span and the tie-back stays. Then we can stay a continuous girder in addition, either from underneath or from top. And thirdly, a special category are pedestrian cable-stayed bridges. And those basically 3 types I'm going to line out. We start with series of cable-stayed bridges. Now, series of cable-stayed bridges typically are several main spans, one after another. Now, if we place live load just on one of these spans, then the towers bend, the beam has very little bending stiffness, goes up, and the strains, first of all on the tower, but also the deformations and strains on the beam, are much bigger than for the 3-span cable-stayed bridge where the tower head is retained by backstays. The missing of the backstays, that's here the idea. And so we have to find a way to stiffen, to retain the top of the tower, also for such a series of cable-stayed bridges, as we do with a 3-span cable-stayed bridge where we tie the tower directly back to the hold-down pier. That's the name of the game for series of cable-stayed bridges. In addition, because series means several main spans, they are very long, and we have to find a way to cater for the changes in length of these very long beams, 2.5, 3 kilometers, due to shrinkage creep and temperature. Those are the 2 problems we'll have to solve, and I'll show you various possibilities. The simplest is to use, say, individual bridges like this, which stand by themselves. They have a stiff A-tower. If we have a force here, it goes up by the cable and goes in tension and compression into the tower legs. So, the tower head is stiffened, can't go to the sides. Then, in addition, we can make these individual units and place a drop-in span, just a simple span which we drop down. So we have then here joints where we can take the temperature. Very simple system. Enrico Morandi, famous Italian engineer, found this. We'll have that later, some more. In very early, I think 1965, it doesn't say here. And it was 235 meter main span. So a very simple, straightforward solution. The bridge is still there. We had to replace the cables and things, but it's there. It's the basic solution, use stiff A towers. And we see here the whole bridge. It is a major bridge. It says here 1962, very early. We just had the first of the Düsseldorf bridge family done. He really was a pioneer. He was a little bit forgotten, but outstanding man. He used, just by looking at it, he used a hell of a lot of concrete for that. We think we can do it with less material. But 1962 was a very good thing, and it still stands, except for the cables, we would say. So, A towers. Now, another possibility is if in every second span we place a hold-down pier. Then we have something very similar to our regular cable-stayed bridges. And we've actually done it. I told you about the Orinoco bridges. Now that's the second bridge across the Orinoco. And ship traffic required 2 traffic lanes in the range of 300 meters, I think it is. Separated because there's an island. Okay, so one could place 2 cable-stayed bridges back to back. We need then here a vertical hold down, perfectly normal. We've retained the tower head by the backstays. Now, since this is also a railway bridge, I told you about building railway bridges there in Venezuela. Railway bridge have very high braking force, much higher than roadway. Whenever you will have to do with a railway force, okay, the load is higher and things, but the main problem is the braking. Now, if we have a long train here and they have these heavy ore trains there in Venezuela with real high braking forces, then we said, okay, we, instead of having a vertical tower, we use an A-frame here. And this A-frame then can take all the braking forces over the whole length of the bridge. We can then use various ways of tying back or connecting the tips of the towers. We can use a straight line, we can tie the tip back here to the next one, or we can overlap. Here the problem is that these are considerable spans often. Now, if you remember the sag and the effective modulus of elasticity I told you about. Now, the less tight we make this cable, the bigger the sag will be, the smaller the effective modulus of elasticity, the less effective these cables are. Well, say, okay, use big cables and pull. Easy, but then where does this force go? Well, it has to be carried all the way back in the beam. And the more I stress it there, the more compression I have in the beam, which costs me, again, money. So it's a little bit playing around, and I show an example. This is actually only a design for Poole Harbour Bridge in the south of England. It's now 2 triangular flaps of a bascule bridge which is built. But there was a design which, if you look very closely, used a series of cable-stayed bridges, and the tower heads were to be connected by horizontal cable. Built is the Munksjö Bridge in Sweden. If you look closely, there you see several main spans, and here is a twin cable which ties together the tower. So those are examples. Examples for tying the tower head to the next tower at beam level is the Ting Kau Bridge in Hong Kong, which Schleich-Bergermann did. You see here, it looks a little awkward. The big tie-back cable has a visible sag. Otherwise, again, the forces would have been too big. And it sticks out like a sore thumb. It's optically or visually it's a little bit questionable. Unique also that the towers are also stayed transversely. Towers are slender, and in order to keep them transversely, they are stayed transversely. You may remember our very first lecture, I talked about the French name for cable-stayed bridges, pont à haubans, and I told you that haubans are what we call in German Wanten, left and right of a sail ship mast to keep it in place, shrouds in English. And that's a cable-stayed bridge which uses this system of transversely staying. The third possibility was purely theoretical until what? 2 years ago. When I made the first draft, I had the system in but had no example. But then Ove Arup made a design for a new fourth road bridge in Scotland and used this type with overlapping stay cables. I said, beautiful. Now I have an example for this theoretical thing. There were two bidding groups, and we were lucky enough to be with the winning bidder, my company, and we are currently doing the detailed design for this one. It seems to work. Overlapping of the stay cables in the center. Next possibility is to use a frame system connecting the beam and the tower. One can then play with the stiffnesses. You can either say we make a strong beam and just hang it up on a small tower, or we say we make very strong towers and hang up a light roadway slab. And that is really playing with the stiffnesses. It's not so very obvious if you look onto the system what it is. One example is the Guangfu in Taiwan by famous in the US engineer T.Y. Lin. Here he's very young. I know him when he was older, typical outstanding Chinese engineer, lived in the US all the time. Outstanding ballroom dancer. When we had some festivities, he danced very well, T.Y. Another frame system is the Arenas viaduct. That's the Spanish engineer, Arenas. Or Mezcala Bridge, all in Mexico, for a new highway across Mexico. There they have had to cross wide valleys. Composite designs, all concrete slab, steel, and frame action in bending. This whole thing works. One just has to calculate it. Another very interesting bridge is the Suniberg Bridge by Men. He's not here, we had him somewhere else. In Switzerland, it's up. If you go to Saint-Maurice, across a valley, and there they had to go. It was architectural considerations by the engineer which drove the design, and they said, okay, we have already very high, 140 meters above ground, so we don't want again some 100-meter high tower that's in the beautiful Swiss Alps. Doesn't look nice, so we want this as low as possible, towers sticking out above the roadway slab. Of course, we want a very slender roadway slab, and so came out something which we could also summarize later on as a very bad word, extra-dose cable-stayed bridges. I prefer stayed from above, but anyway, it is something like that. It's a mixture between a continuous girder and additional stays on top of the piers, and the whole thing was curved, and you had to adjust the stays to the curvature, and there are deviating forces, and it's quite involved, and it's a very nice, technically interesting design, and an excellent solution for this beautiful Alp valley in Switzerland, what men did there. Now, one of the biggest, most imposing recent series of cable-stayed bridges is Rion Antirion in Greece. We will have, it is part of a special lecture in the next semester where I show you in detail how that was built. Very difficult earthquake conditions. The beam is continuous over 2.5 kilometers, hanging only in the cables, no vertical support. Plus minus 2.5 meter movement joints at the end for temperature and shrinkage and creep. It's composite, and the towers stand by using A-frames in both directions, A-frame longitudinally, so we can take it here, but also A-frames transversely for the wind. So we have, if we want to use the word quadruple legs, we have 4 legs on each tower, and every section stands by itself. Basically, French design. We'll have the picture later. Well, no, here it is. Jacques Combeau, friend of mine, was the guiding light, and it, especially with the very high earthquake forces in Greece, difficult thing. So we'll have, half a lecture. We have 1 lecture on series, where the first half is on Millau, which we see now, and the second half is on Rion Antirion. Here was Jacques Combeau. Another interesting in this connection is the crossing of the Baltic Sea, 19 kilometers, which is under design. And our group designed a cable-stayed bridge with a truss, using a different tower design. Basically, it's 8 towers standing by themselves. However, due to political reasons, most probably the tunnel will be built and not our beautiful bridge. Well, such is life. Other possibilities of using frame actions I'm showing, and in addition, I mentioned we have to cater for the changes in length. Well, if we have a drop-in girder, or just a joint, the driving comfort suffers, because whatever you do, you will always get the feeling that there is some sort of a joint if you don't have a continuous. The worst is in precast slabs. Somewhere in Italy, the Autostrada del Sole, where you go bong, 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 bong. So it's better to avoid these joints, at least if they make a kink due to creep or whatever. Now, it is possible to use a joint which is stiff in bending by using, for example, 4 positions here where to support such a beam. It's a little theoretical. It can be done, but I don't think it has ever been done. So the best is avoid the joints. Now, these stiff elements where we have the problems with the length of changes of length of the beam can have 2 requirements on the towers. On one hand, the tower must be able to carry live load just in one span, so it must be stiff. I told you a tower, but you can make it also very stiff. On the other hand, because of the changes in length of the beam, and we try to avoid the joints, these towers must be flexible horizontally against changes in length, temperature, shrinkage, and creep. Well, there's one known solution that we split up the tower in the lower part like a washing cloth here. Now, if we have a load, the force runs up here, the moment goes down, then the moment is split into a force couple in compression and tension going down these two halves of the beam. But because the lower part is split in two, it's very soft horizontally. We know the system from free cantilevering. When we free cantilever out, we can take the moment, but we are also able to move horizontally. So that's the trick here. Stiff above, split the moment in a force couple, tension and compression, but be able, because once you split it, the stiffness horizontally is very low, so it can move with shrinkage and creep. That was an old design by Finsterwalder for a crossing of the Great Belt, 1967, but it's a very nice idea. Other systems, I'm just thinking, modern days, the same idea has taken up by Velojeux in France for the Millau Bridge, which we also have a special lecture on, required a very long crossing of the Tarn River in the south of France. And it is done. We have an A tower, which is stiff in bending in this direction, we know. And then we have the up to, I think, 270 meter high piers, which are split. You can see it here. You can see it here just split in two parts. Again, the moment from the A is going into the two legs of the split tower in tension and compression. And the whole 2.5 kilometers beam are continuous. Their fixed point is basically in the center. And from there then the beam moves in and out with temperature. It's a steel beam. But the split piers, split in the top half, can follow. That's a trick. We will see that in some detail. Another possibility, briefly, in Macau, one has used simple backstays and forestays and has placed two together so that the backstay from here goes to that. So that's a stiffened frame here, and here we have the spans with a drop-in girder. A very basic solution, but it works. Okay, here we have Michel Velojeux, the engineer of the Millau Bridge, and the architectural advisor was famous English architect Sir Norman Foster. I stress, however, contrary to some publications, Foster did not design the bridge. The bridge was designed by Michel Velojeux, but Foster gave a hand in shaping that thing beautifully. Okay, now those were series of cable-stayed bridges. Now we come to stayed beams, as I called it. We had the problem in the, when was that? 78, in the 70s. Freeway from Stuttgart down to the Lake Constance, Bodensee. Large valley, Neckar Valley, and the slopes were supposed to creep, so no piers down there. So that meant we had side spans of up to 260 meters with inner spans of 180 or something. Now, that's extremely awkward, and we wanted to have a constant depth beam and all that. I was involved, so I know the story, but finally the idea came, okay, we stay these end spans from underneath. You see? And it stays with the king post in between lock coil ropes, and that works very nice, especially for permanent loads. For permanent loads you have the side span, so instead of 260 meters we had 130 here. That helps a lot. It's not very effective for live load. It helps only a little because the stiffness of these stays is small compared to the stiffness of the beam, so the increase in bending stiffness is not very big for live load. But for permanent load we can pull as much as we want. Helps. Famous example, one can go a step further, also in the south of Germany, across the Argen Valley. One was not supposed to go into this slope, and so Schleich then had the idea to make a cable-stayed bridge here, and so to say continue the stays to make an underslung cable-stayed bridge. Nice idea, very difficult to build. The contractor was very unhappy afterwards because the thing works only once it is completed. That's always a problem if we design bridge systems which are not stable during construction. Contrary to cable-stayed bridges, when we free cantilever out, it's stable. But this thing isn't stable, and then they couldn't go in here. It was a mess, but finally it works, of course, very nice. Now, then you may have heard the word extra-dosed beams, which is a stupid word. It was invented by a Japanese who couldn't speak English, but it has been taken out. All it means, it's a beam stayed from above. Now, what distinguishes an extra-dosed beam from a cable-stayed bridge or from a continuous girder? I try to explain it by basically the shear transfer from a load on the beam. If we have a cable-stayed bridge, we can consider hinges where the cables meet the beam, and all the force is transmitted via the cable to the backstays. Nothing runs directly, nearly nothing, runs directly from the beam into the tower pier. If we have a continuous girder, maybe haunched, naturally everything what I place on a load runs via the beam to the piers. Now an extra-dosed bridge is in between. If we place a load there, if we place a load somewhere here, then part of it runs via the cables, but part runs, because we have a stiff beam even with a haunch, through the beam. Typically 50% goes through the cables, 50% through the beam, and the extremes being cable-stayed, nothing through the beam, or continuous girder, 100% through the beam. So at least that you know, most people don't know what they are talking about when they talk about these darn extra-dosed bridges. That you at least know what is the idea behind. It was invented in Japan, used in Japan. It has its advantages if you want to use, if due to some reasons you have a very deep beam. But it's not fully enough. Then you say, okay, instead of having a bigger haunch, I have some stays on top. Maybe economic. So an important example is the Golden Ears Bridge in Vancouver, BC, built by Bilfinger. I was checking engineer, and it's very difficult soils condition again. You see here the trick. We have a stiff tower on top, but we have a split pier to be able to take the horizontal movements with a split pier. Another one, Tisza Bridge, I was also checking that just for good measure. And finally, we go to cable-stayed pedestrian bridges. Now, I used to say pedestrian bridges are the playground of bridge engineers because the loads are comparatively small, pedestrians, and the spans are not the real big ones. You can really play around, and unfortunately, I say, it leads that there are many pedestrian cable-stayed bridges which have the wrong flow of forces, which are designed as a sculpture, beautiful, but the flow of forces is wrong. And I have always rejected to say, make a design by an architect which I don't think proper to help to make that thing stand up. Of course, with brute force, you can do all sorts of things. But so there are 2 books out by Schleich Senior, Jörg Schleich and Mike Schleich, both called Pedestrian Bridges, Fußgängerbrücken, and they give a real big picture of all the playground things there are. I just make it rather small and show more or less rational cable-stayed bridges. If you want the wild ones, you have to go somewhere else. I'm not the one for the architectural sculptures. The Schillersteg in Stuttgart is one of the very early cable-stayed bridges, especially the first one using the new type of stay cables, parallel wire cables, designed before 1960. Early on was the first use of BBR, parallel wire tendons, very slender deck, 50 centimeters, very thin steel plates. If you go across, one person excites it, and first the people were not happy because it was too wobbly, but now everybody knows, and one doesn't talk about. You cannot, and we've tried it, you cannot get it really moving. We had a group of our engineers and draftsmen there, and 1, 2, 3. You can't. It has also to do that the eigenfrequency changes with the amplitude. It's a nonlinear effect. When you get more and more cables stronger involved, the complete system beam and stay cables swinging changes a little bit the eigenfrequency, and that alone you cannot follow with your people jumping on there, and we've really tried hard, but we couldn't do it. It was only 20 to 25 centimeters, and then it broke down. So in reality, if you have these wobbly bridges, if they are designed properly, you cannot really excite them. It's not the big danger. The papers sometimes write about soldiers marching in step and all that. You get some additional forces, but not so very much. Well, on Tuesday I have to talk about that because in TV what I mentioned, because the Nienburg Bridge broke down because people were jumping to the tune of a song there, and that gave it was overloaded anyway. And that was the last one, 1825. And that 55 dead in the Saale River, and that stopped cable-stayed bridges for 125 years, not only in Germany, but somewhere else. Navier said, no good. I've told you all that in that lecture, but you may not remember. Anyway, Schillersteg, very early, very light, first use of parallel wire stay cables. Another light one, new insofar that it used in the main span lightweight concrete. For some time in the 70s, it appeared that lightweight concrete may be the one to use in future. And it was used, we had a Rhine bridge, Köln-Deutz, where the center part is lightweight concrete, some others. This was lightweight concrete precast elements. But time showed, the characteristics are not so favorable. It's less strong because of the lightweight aggregates. And it's expensive, so it's probably it's more or less out of the market. But in the 70s, it appeared it would be a good thing. And so this is, I think, the only cable-stayed bridge with a main span from lightweight concrete, and all sorts of investigations on shrinkage and creep was done. Neckar Center Bridge in Mannheim was technically interesting. I mean, it has 140-meter main span just for pedestrians, a slender, I think 60 centimeters, I can't read it here, solid cross-section, central cable plane, steel towers, a hinge here, a viewing platform around, a nice, made for pedestrians, a major cable-stayed bridge. In Pforzheim, also in Swabia, South Germany, this cable-stayed bridge, due to the local conditions, has to have two kinks, at least one real kink here, which I think is unique. I'm not aware of any other cable-stayed bridge with a kinked beam. Naturally, it gives us some additional moments from the compression forces, which are highest at the tower, but pedestrian bridge, I mean, the forces are not so high, and one could cater, but that's the unique feature of this bridge. And finally, there's a Galgenbergbrücke in Weibling, again, a very thin cast-in-place concrete slab with a straight A tower, and what we use in our office very like that, this railing with just vertical bars and one top element there, and in a light red. We like that very much as a light pedestrian railing. Then Ravensburg was a special situation. There is an open tunnel. The tunnel is behind the truss here, and a cable-stayed bridge had, pedestrian cable-stayed bridge had, the third one is missing. And there's another curved truss pedestrian bridge in this region. And these basically very different structures. Cable-stayed here, a side truss and a curved truss supported. They were bound together visually, I would say, by using the same bright red color for the steel parts. So it's an architectural feature. I think, well, I have it now in the book, it's section 2.1. In the presentations we have it at the end. I think it's lecture 29 when I talk about guideline for bridge aesthetics. We'll have that again and I show you that. An important pedestrian bridge across the Rhine River at Kehl. I'm just thinking what we've got. That comes again in bridge dynamics. There are very few pedestrian bridges across the whole Rhine. You know, the Rhine River is the largest span in Germany, and this connects the German city Kehl with the French city Strasbourg. And as usual in France, the architect is in the driving seat very often for bridges. The architect designs the bridge and he gets an engineer to help him make it stand. So the design was by a French architect, and we were supposed to calculate it and do it. It's tricky. It's two halves. One goes here from the river to the river, and if high water, people can't walk there, then they can use the levees. And the second half goes here from top. The whole thing is curved, very light. Some special damping measures were required. It looks beautiful. It's a daring structure. We'll see it later on a little bit better. And finally, a little cable-stayed bridge, nothing really particular. No, we don't have it here. The tower rests on a steel sphere, so we have designed a real hinge there. It was helpful during construction. So that's what I wanted to show in cable-stayed bridges, in cable-stayed pedestrian bridges, knowing they are not very spectacular. If you want the real spectacular, go to some other sources. I'm just a plain engineer. I like these plain bridges. So, to sum it up, we had special types of bridges. We had the series of cable-stayed bridges, many spans, where we had to consider how we stabilize the tower head. We can do it with an A, we can tie it down, or we can make it stiff on top, split the bottom pier, and thereby have bending stiffness, but shear it's soft. Those are the basic ideas. Then we thought about beams which are, I say, strengthened by stays, either the span, if we have long end spans for a creeping slope. We can have a king post in the middle, tie it back. Or if we want to increase the capacity of a beam on top of a pier, we can place a few stays on top and call that, some people call that extra dose. And finally, a place by itself are the pedestrian cable-stayed bridges, because there the rational demands on flow of forces and economy, which govern otherwise our cable-stayed bridges, are a little bit relaxed, and we can play there and do nice-looking things, maybe not the best flow of forces or the cheapest, but maybe very nice-looking. Thank you very much.